Good morning, everybody. Here we go. Today for you is Tuesday, September 22nd, and we are finishing up section 3.2 today, 3.2 day 3, and we're going to talk about the symmetric difference quotient and the numerical derivative. I'm going to have to kind of go rather quickly today. If you missed something, remember this is up on YouTube. You can go look it up and listen to it again, or we can talk sometime on my Wednesday evening review this week from 6 till 8, or you could come to second hour. Actually, I should be in second hour today, Tuesday, and I'll be there second hour on Thursday as well. So hopefully we can get things straightened out if you're not kind of keeping up with everything so far today. All right. We have the same kind of idea going on. We have some function y equals f of x, and we've got some spot A, and we are interested again in talking about the slope of the tangent line at x equals A. And if you go ahead and draw that in, tangent line at x equals A, I line that up right there. There's the tangent. Okay. Then let's take this A, and instead of just going in one direction like we did the last time where we added on an H and went from there, we're going to add on an H, and we're also going to go backwards some amount. So let's add on an H here, and here let's also make that distance H, which means that this x coordinate now is some A plus H, and this x coordinate right there is some A minus H. We went up to A and then backed off H. If we take those two values, that A plus H, and we line it up to where it hits the function, and this A minus H, and line up to where it hits the function, excuse me, this point right here now has coordinates A plus H, comma, f of A plus H, and this point has coordinates A minus H, comma, f of A minus H. And let's draw the secant line in between those two. There's the secant line. All right, now we've been doing this for a while now, so looking at this, you should be able to come up with an expression for slope of the secant. And that slope of the secant is difference in y values from here, so f of A plus H minus f of A minus H, all over change in y values, A plus H minus an A minus H. And when we simplify, nothing happens to the numerator. The denominator simplifies. The A's subtract out, and we have H minus a negative H, so 2H. This expression right here, f of A plus H minus f of A minus H all over 2H, that is called the symmetric difference quotient. That sounds very similar to what we've been talking about, but different still. What's different? What's different? Okay, 1, there's no limit. And before we called them standard difference quotients. We only had an h up here instead of a 2h, and we had a limit, and we had standard difference quotients. For this symmetric difference quotient, what we say is that as h gets sufficiently small, the symmetric difference quotient approximates the slope of the tangent line. Very similar to what we were doing before. Very, very similar. Instead of going just in one direction, we're going out in two directions. Why it's called the symmetric difference quotient? Because you're going the same amount on both sides. You're going h on both sides. So symmetry going on here. What's ambiguous about this is this sufficiently small idea. How small is sufficiently small? What does that mean? How small is sufficiently small? And what can happen is that the size of that h can be chosen. And the size that you choose is called the tolerance. And tolerance, kind of like how much error are you going to tolerate, if you will, or how close do you want to get? What will you allow? What will you tolerate? Again, if I'm going too fast, you can ask the substitute to pause and you can catch up, or you can go up on YouTube later on and search this out. The title would be probably AP Calc 3.2 Day 3. Okay? All right, here we go. Let's look at this one. Uh-oh, something's wrong. I am missing a page. Am I missing a page? No, I'm not. I thought I missed a page. Never mind. Sorry. Okay, so we are going to approximate the slope of the tangent line to y equals 3 square root of x minus 2x plus 1 at x equals 16 if h is 0.1 at your tolerance. That's your tolerance. So we are going to do f of a plus h minus f of a minus h all over 2h when x is 16, that's the a value, and the h is the tolerance. So this is going to be f of 16 plus 0.1, so 16.1 minus f of a minus h, 16 minus 0.1, so 15.9, all over 2h, or 0.2. Okay, go get your calculators out because I'm going to show you how to do this on your calculator to save a little bit of time. Take your calculator out. Don't just watch me do this. Come on. Take your calculator out. Oops, I gotta find where you can see this. Let me translate on, see if that helps. Ooh. Turn the brightness up. Does that help? I think so. I'm checking it on my screen, so I think it helps quite a bit. All right, so here we go. I want you to put this original function into y1. So 3 square root x minus 2x plus 1. Okay, go back to a home screen. Let me clear that out so you don't see that from yesterday. All right, now, your calculator does function notation, and you can actually type this in one big long string. You can use the fraction bar and everything, so fraction. Now, f of 16.1, well, that function is typed in y1, and you can get y1 by going alpha f4. Again, alpha f4, there's y1, 1. We're going to evaluate that at 16.1. Doesn't that look like function notation? y1 of 16.1 minus alpha f4 to get the y1 at 15.9, all divided by 0.2. Function notation on your calculator. There you go. Hit enter, and it gives us that big long icky decimal, and I do want you to write down this big long decimal. This is negative 1.624998169. Okay, now we're going to do this again, but we're going to do this with h is 0.01. So f of 16.01 minus f of 15.99 all over 0.02. And what makes this idea nice is you can just arrow back up and grab that expression again, and then let's just go back and insert some zeros and some nines. So right here, I'm going to insert a 0. So I got the cursor on the 1, and then insert is second, delete, insert, 0. There's your 16.01. Then I'll have to retype everything. We're going to insert, oops, I want to go one farther. Insert a 9, there's 15.99, and then insert a 0 here. Uh-oh, where'd it go? Oh, I know. 0, 2. That's easier just to type. Okay, enter. And there it is. Negative 1.624999982. 4 nines, yep. Okay, one more time. H is 0.001. So here we are, f of 16.001 minus f of 15.999 all over 0.002. We will get negative 1.625. Okay. Boy, that's a pain in the neck, isn't it? Absolute pain in the neck to type all that stuff in all the time. Whew, boy. You are so lucky because your calculator has this program built in. Wahoo! All right, here's where you can find this calculator. Under Math, 8. So Math, and then the 8th one down, and Derive. Or you can get it much faster if you have the alpha functions in here. So alpha, F2, and right there, number 3, and Derive. And that's the one that you want to choose, and Derive, and it looks like that. This program is set up in your calculator as the symmetric difference quotient, Uh-oh. Symmetric difference quotient with a tolerance of 0.001. With a tolerance of 0.001. So it's this idea set up. All right, we have a few notation issues that we need to talk about. And the first one is that when you're expected to use your calculator to do this numerical derivative, your textbook writes this. N dir of f of x comma x. When you see that in your textbook, that means to use your calculator to find the slope of a tangent line. Calculator syntax is what this looks like on your calculator screen. What are you going to type in? And it looks like this. Oops. You're going to type that x. When you type it up on your calculator screen, it doesn't look ddx right away. It looks like this, dd, and there's a box here that you're going to fill in, and then parentheses. And then there's another box in here that you're going to have to fill in. And then there's going to be a big long vertical line. And then you're going to see a little box over here and an equal, and then another box over there. Let's just double check that that's what you see. 3. There it is. Do you see it? It's afternoon here, so my room is very glary. That's the sun shining in from the windows. Sorry about that. DD, that's you're going to fill in. That one you're going to fill in. Notice this box is solid. I'll explain to you why that is in a minute. And then that box is dotted as well. Okay? And what's going to happen, what you're going to fill in here, is that you are going to type an x there. You're going to put the function here, and you're going to put a number here. Okay. These three boxes are all dotted on your calculator. This one's solid. Here's why. When you type that in your calculator, let's just go ahead and put an X down here, and as soon as I put in an X, I want you to watch that solid box. Oh, look at that. It changed automatically to an X. So that's why that box wasn't dotted. It was solid because it's going to fill something in there, but you don't get to choose it separate from this box. Basically, your calculator is going to fill into that box whatever variable you put here. Okay, so far? All right, so now let's go back and let's do this actual problem that we just did. Find the slope. Let's find the slope of the tangent line at 3 square root x minus 2x plus 1, and let's do this at 16. So we've got it started. We need to put the function here. Now you can retype what was here already, this 3 square root x minus 2x plus 1, but that's already typed into your calculator somewhere. That's already typed in at y1. So you might as well go ahead and use that. Alpha f4, again, pull up that y1. So d dx, y1, when x is, there you go, put that 16 in. Ah, magic. That's the slope of the tangent line, negative 1.625. Isn't that awesome? Are you ready to throttle me because I've been making you do this the long way and your calculator finds slopes of the tangent lines automatically? I bet you are. That's why I planned to be gone today, so that you wouldn't be too mad at me. Do you believe me? Do you believe me? No, believe me, I would much rather be there with you right now than sitting in the goofy meeting that I am sitting in. All right, so let's look at another example and see if we can use your calculator to do this. Okay, so we're going to look at this parabola, y equals 4x squared minus 9x plus 12. I want you to find f prime of 9. That's slope of the tangent line when x equals 9. There are several ways to do this, okay? First, because we're going to be going from a graph in a couple of minutes, so let's go ahead and put this function into y1. Let's go ahead and clear out that old one and let's put this new one in. 4x squared minus 9x plus 12. Okay, so now it's there. We're going to do this from a home screen. So let's start here on this home screen. And you're going to do n derive, so math 8. Or you could do that alpha f2, number 3. And what we're typing in, what it's going to look like, d dx. You're going to put that x in. y1. I am writing it down here, and you should write it down on your notes as well, so that later on, if you forget, you always have something to go back to. When x equals 9. So d dx, and then our y1. Let me move this so you can see it better. Is that better? y1 at x is 9. No, what's that? 63. That's the slope of the tangent line. This is 63. Okay, now, some of you have the old operating system and you're probably just a little bit panicky. Let me clean this up for you in case you have the old operating system. If nobody has an old calculator, well then I'm sorry, you're going to waste 30 seconds of your life, but that's okay, you'll survive. All right, in the old operating system, you have to do math 8. And then your screen comes up like this. N derive with the parentheses. And what you are going to put in here is the function, comma, variable, which is x, comma, number, and then close parentheses. If you have to do this, the comma is right here, right up above the 7. Okay? All right, now from a graph, what we can do is, let's graph this baby. Ooh, there it is. But let's open this up a bit because our window is too small. So let me adjust. Oh, negative 10 to 10 is probably pretty good. But I think we're going to need more y values up here. So let's send it up to 100 in the y's. Here we go. Okay, from a graph, go to Secant Calc where you do all your max, mins, and intersects and all that kind of stuff, and look at this 6th one down. So if you go to Secant Calc, and then number 6, dy dx. So if you choose that one, 6. Now it doesn't show you anything. It looks kind of freaky at first, like, oh, what did I just do? Well, type in the x value, just like you were doing a value. So type in a 9 here. And look at that. Look how pretty this is. Look what it just told you. When x is 9, y is 255. And also right up there, dy dx equals 63. Woo! Perfect. Perfect. Okay. Now write the equation of a tangent line. So from the graph, we got that information right there. We just found all that information. So y minus 255 is slope 63 times x minus 9. Okay so far? All right, now go to the draw menu. Draw is right here. It's second program. So second program, draw. We'll look at this one down here, 5. Draw a tangent. Now we want to draw a tangent at 9, so we'll just hit 9. Oh my, look at that. Holy criminy. There's that tangent line sitting right there, but we can't see it right now. Why not? Why can't we see that? Yep, because the y value is way up here at 255, so I can't see it. Let's go adjust. Oh, but look at this. Oh, no way. X is 9, y equals 63x minus 312. Oh my goodness. And type that number. So you went to draw, the draw menu, which is second program, then tangent, and then you had to type in the number that you wanted, and holy criminy, this is so exciting. Y equals 63x minus 312. Aren't you mad at me? Ha ha. Oh, just wait until tomorrow. All right, let's clean this up so we can see this a bit. I'm going to change my window here. Let's send this up to 300. So I hopefully can see that tangent line. Oh, you know what? We're going to have to clean that up too. We're going to have to take this out a little bit farther. Take this out to 20 for the x's, and let's send the y's up even higher still. Let's go up to 400. Okay, now we do have a problem here. And our problem is that we had that tangent line on there, but now it's not anymore. And that's because it's not drawn off the function menu, it's drawn off the drawing menu. So you basically have to tell the calculator, yes, I want you to draw that again. So here we go again. So second program, which is draw, tangent, fifth one down, and then you have to tell the calculator where do you want to draw the tangent line at. And at 9. Cool. Cool beans. All right? A little bit more, just this last little bit down here. I know I'm throwing so much at you today. You're going to have to spend some time and do the homework and do the recommended problems, etc. We can also graph the equation of the derivative without actually figuring out the equation. So for this one, y equals a third x cubed and its derivative. So y1, I want you to put 1/3 x cubed. Go ahead and do it right now. 1/3, I don't want to do fractions, so what if I do this? X cubed divided by 3. Isn't that the same thing as 1/3 x cubed? Okay, in y2, I want you to do the derivative, so d dx of y1 at x equals x. So alpha f2 3 d dx y1 at x equals x. Okay, listen carefully. Stop writing. Listen, listen, listen. Eyes up here. The only time that you will put x equals x is when you are on a graphing screen. Otherwise, never, ever, ever do x equals x. The only time you do x equals x is if you want to graph the derivative. Otherwise, you have to put x equals a number. Okay, so let's graph. Let's flip back to a standard viewing window, zoom 6. All right, there's 1/3 x cubed. And the derivative graphs very, very slowly, because what the calculator is doing is it is calculating the derivative at every single point along that curve. Every single point. So it's doing a symmetric difference quotient at every single point along this curve. Symmetric difference quotient at every point. So that's why that derivative graph's so slow. I'm sorry, I got to move this out of the way so I can draw this. And I do want you to draw it onto paper. Doesn't have to be perfect, but I would like you to get a sketch of this on here. My original function was in blue, so I'm going to do this. It's a lighter blue, but I'm going to do it in blue. There's y equals 1/3 x cubed, and then the derivative is in pink. And these do intersect out here. Oops, that was too wide. I'm going to have to clean that up. That one goes like that. Okay, this pink one is y equals f prime of x. That's f of x, that's f prime, that's the derivative. Okay? All right, one last little bit for us. Caution, 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 caution. Big flashing lights around this thing. Caution. Caution, yellow caution here. I want you to use your calculator and find y prime at 0 for the absolute value of x. We're going to do that off the home screen. So alpha f2, 3, and derive. I'm going to type this one in because it's real quick. Absolute value. Do you all know where to find absolute value on your graph? Oops, wrong way. I'm trying to be straight for you guys. Absolute value is under math. Arrow to number. And then first one, absolute value. Again, you have to go to math, then arrow over to NUM, which is number, and then the first one down is absolute value. So x, oops, back, at x is 0. And that tells us the slope of the tangent line of the absolute value of x when x is 0 is 0. Again, I'm just going to show you what you typed in on the home screen. Another loop there. That bothers me. It doesn't bother you, but it bothers me. Home screen, you did dx of the absolute value of x when x equals 0, and your calculator told you 0. Okay? Alright, look at the absolute value graph. Isn't this the graph of y equals the absolute value of x? Yep, it is. Y equals the absolute value of x. Okay, at x equals 0, what's the slope of the tangent line? There isn't one. Why not? There's a corner here. There's a corner. Because the slopes of the tangent lines from the left do not equal slopes of the tangent lines from the right. Okay, this said the slope was 0, but we know that the slope doesn't exist at x equals 0, and there is no tangent line at x equals 0. because the function is not differentiable there. There's a corner. Okay, so that is not the slope at x equals 0, because y equals the absolute value of x is not differentiable at x equals 0. There's a corner f prime from the left side of 0 does not equal f prime from the right side of 0. Okay, quickly. So why did this happen? Why does your calculator goof up? Well, your calculator didn't goof up. The calculator did exactly what you told it to do, which was to evaluate the standard difference quotient at x equals 0. And remember, what does a standard difference quotient do? It takes a point, it goes out 0.001 to the right, it goes 0.001 to the left, finds those two y values, and calculates the slope between those two y values. Let me show you again what your calculator does. It goes out 0.001, goes out 0.001 to the left, finds those spots on the curve, finds the slope of the tangent line between those two spots. Absolute value, won't that be a horizontal in there? Absolutely, because of the symmetry of the graph. So this is giving you the slope of the secant, not the slope of the tangent. Symmetric difference quotient is not infallible. You have to think. Don't trust everything that your calculator says. Your calculator is not wrong. It's doing exactly what it was programmed to do. You just have to understand how it works and that it is not capable of independent thought, so you have to think for it. Whew! Okay, thank you very much for your attention. I will see you on Wednesday.